Let's take a look at the chain rule now and see why that's true. So the chain rule says d dx of f of g of x equals f primed of g of x times g primed of x, or another way of expressing that is df dx equals df dg times dg dx. So we know how to take the derivative of a function of a variable. That's just d dx of f of x equals this limit definition here, and this is the alternate definition of the derivative, where instead of taking a limit as h or delta x go to 0, we take a limit as t goes to x, and we have this here. That's the alternate definition. So the chain rule tells us how to find the derivative of a function. So if we stick a function inside of another function, like here, we're using a function g of x as input to the function f. And the chain rule tells us how to take a derivative of that. Well, just from the alternate limit definition here, we're still going to take a limit as t goes to x because x is still our independent variable. So we still take a limit as t goes to x. And then what we have is f of g of t minus f of g of x all divided by t minus x. So how do we work with that? Well, let's bring that to the next page. Then what I want to do is multiply the top and the bottom here by g of t minus g of x. And then what I'm going to do is in the denominator, I'm going to switch the g of t minus g of x with the t minus x. So all I did was just swap those two around. Now the limit of this product is the product of the limits. And this limit right here, this is the derivative of g. It's g primed of x. It's just the alternate definition of the derivative there. Now what's going on over here? Well, as t goes to x, what happens with g? Well, as t goes to x, g of t goes to g of x. And we know that's true because g is continuous, and that's what it really means to be continuous, is that as t goes to x, g of t goes to g of x. And we know that g is continuous because g is differentiable, and g has to be differentiable, otherwise this doesn't even make sense to talk about. So anyway, so since t goes to x implies that g of t goes to g of x, then this limit, we can rewrite that as the limit as g of t goes to g of x of the same expression here. So the expression in the limit didn't change. Just what we're sending to something else here, that's what changed. So as t goes to x, g of t goes to g of x. Now what I want to do is make a little substitution just to make things a little bit easier to look at. So g of t, I'm going to call that s, and g of x, I'm going to call that y. Now the only reason we're doing this is so that we can put this in a different form that's much more familiar to us, much more easy to look at. So this right here is the alternate definition of the derivative. This is going to be f primed of y. So we end up with f primed of y times g primed of x. Now let's go ahead and undo our little substitution. Remember, y took the place of g of x. So we undo that, and we end up with f primed of g of x times g primed of x. Okay? So again, that little substitution wasn't really necessary. The only reason we did that is so that we can take this complicated expression right here and make it a little easier to look at, a little bit simpler, so that it's more familiar, and we could look at this and more easily recognize that as the alternate definition of the derivative. So we ended up with this right here, which is what we wanted to show, but if only it were that simple. So there's actually a problem with this first step here. So in the first step, we multiplied the top and the bottom by g of t minus g of x, and we continued from there. But that's not good because we don't know if g of t minus g of x is equal to 0 or not. And if g of t minus g of x is equal to 0, then we have problems. We're not allowed to do that because we can't have 0 in the denominator. Because if g of t minus g of x is 0, then we're dividing by 0, and that's not okay. Now you might be wondering, well, don't we have the same issue with t minus x? And we don't, because when we take the limit as t goes to x, we always have t not equal to x. So since t does not equal x, t minus x never equals 0. So that's not an issue. But this over here, that could be an issue. G of t minus g of x could be 0. So most of the time, quote unquote most, I guess, this is not really an issue. For most functions that we encounter in practice, it's not really going to be an issue. So when we take the limit as t goes to x, we really only care about what happens as t gets really close to x. So unless our function g is crazy in some sort of way, then we'll most likely be able to get t close enough to x so that as t continues to approach x, then we actually don't have g of t minus g of x being equal to 0. So in other words, we could get t close enough to x so that this expression, g of t minus g of x, is never 0 anymore. And most of the time, for most functions that we encounter, we will probably be able to do that. But we're not guaranteed that we can do that. So such crazy functions do exist that won't allow us to do that, or to say that. And we do need to account for those crazy functions. So for example, it's possible that as t approaches x, perhaps g of t oscillates infinitely around g of x. And in that case, we're kind of stuck. There's nothing, well, we can't use this method here. So for a more specific example, let's say we have this piecewise function g of x equals x cubed times the sine of 1 over x if x is not 0, and it equals 0 if x equals 0. So this function actually oscillates infinitely around 0 as x approaches 0. So for this specific g of x, the chain rule explanation that we gave on the previous page, or earlier pages, it's not going to work for the derivative at x equals 0. It won't work because we have this infinite oscillation here. We can't multiply by this expression because as t approaches 0, g of t minus g of 0 takes on the value 0 infinitely many times. And this is true no matter how close t gets to 0. So no matter how close t gets to 0, there are still infinitely many more values of t along the way to 0 that make g of t minus g of 0 equals 0. And here's a graph of that function g of x. So we can see that as our independent variable x or t, whatever you want to call it, as it moves closer and closer to 0, we have all these oscillations here. And the oscillations get really, really super tiny as we get closer to 0. But really, there are infinitely many of them. As we get closer and closer to 0, the oscillations really don't stop. It just keeps on going infinitely. And that's not really surprising when we look at the definition of g. So here, the oscillations occur because of the 1 over x piece right here. So how do we handle this problem right here? How do we get around that? And that's what we're going to talk about in the next video.